We're now going to record regression diagnostics. We've covered it in the last session. Now I will show you how it is done using real data. So as I mentioned earlier, regression diagnostics is basically done to ensure that the estimates that you get are reliable and can be used for research. So now let me first get a data. Let me get a set of data like I did in my last presentation. Here I have a data on Y. I have a column of ones, which we normally use when we estimate the coefficients of a regression manually in Excel. And my variables are x1, x2, x3, and x4. So I have three independent variables, one dependent variable, and therefore it is a multiple linear regression model that I'm going to now discuss. So regression diagnostics, before we begin, finite or small properties, these are the properties that are applicable to small samples, because when small samples are used to estimate, the estimate should give you reliable values which are true of the population parameter. So the first assumption is the assumption of linearity. That means the relationship between x and y are the same at any level of x. And there's a concept called strict exogeneity, which means that independent variables are strictly independent, which means that this variable does not depend on anything else. This variable depends on x1, x2, x3, x4, but x1 does not depend on anything else. The implication is x1 will not have any error. So it is considered to be deterministic, and that's what you mean by strict exogeneity. Coming to fitting a regression line by the method of order least squares, the error term should be normally distributed with mean 0 and standard deviation sigma e. This is mean sums of squares due to error. This is tested using the Bruce-Pagan test, and the solution is weighted least squares. Now to go back to the data. Now here we have a dependent variable, we have an independent variable, and as I discussed in the earlier class, in the earlier video, what I do is I take the independent variables, including C. I take all the independent variables, I copy it, and I transpose it over here. So I do a space special, and I will do a transpose, and I say OK, and the variable gets transposed. Then what I do is I construct this matrix. This matrix is a product. This matrix is a product of X transpose and the X matrix, which is here. So I close the bracket and I say Control Shift Enter. Then I have got the X transpose X matrix. Now I calculate X transpose Y by, again, with MMULT. It's X transpose Y X. So it's X transpose, this is X transpose, and Y, which is the dependent variable, I'll select it, close the bracket, and it is Control Shift Enter, and this gives me X transpose Y. So now to get the matrix, we have to get the inverse of this matrix. So we have to get X transpose X. I have to get the inverse of this matrix equal to M inverse of this matrix, and Control Shift Enter. So I've got the inverse of this matrix. And now the B coefficient can be corrected directly as the product of X transpose X inverse X transpose Y. X transpose X inverse X transpose Y. So this gives me B. So I will not get into the standard errors and the other things because that's already been discussed. Now I'll straight away go to estimate the assumptions of ordinary least squares. So from this model, I estimate the estimated values of Y, which is nothing but equal to MMULT. It is X into the coefficients, x into the coefficients. Close the bracket, Control Shift Enter. So I've got the x hat, and from this I calculate the error. Before calculating the error, I will remove it so that you see it's being done. So before calculating the error, so it is y minus y hat, y minus y hat. Okay, so I get an error. These are my error values. Right? So I can get the error values. And then I will have a look at the values like I did in the earlier case. I will now get a plot. Get a line, and plot the error term. And the error term looks more or less random. So anyway, that's a visual inspection. And the first assumption that I have to check, the error term, the mean is equal to 0 and the standard deviation is equal to a constant. The command is equal to average. Average of the error will be very close to 0. I get a value, very, very small value, which is 4.6 into 10 to the power of minus 12, which is actually a very, very small value. So when I round it up to 2 digits, you actually get 0. So the mean is 0, and the variance has to be tested. For that, we have to do a test called the Bruce-Pagan test. So we've discussed it over there. It's done. We use what's called the Bruce-Pagan test. Just to know what exactly heteroscedasticity is. So heteroscedasticity happens when the standard errors of the variables are not constant. With heteroscedasticity, telltale signs upon usual inspection of the residual errors is that they will tend to fan out over time as depicted in the image below. So that is what we saw over there. Since we didn't have enough information, it was not visible. Heteroscedasticity is detected using the Bruce-Pagan test. The heteroscedasticity is detected using the Bruce-Pagan test or the Cook-Weisberg test of heteroscedasticity. The Bruce-Pagan test is designed to detect if any linear form of to detect any linear form of heteroscedasticity. You run a regression. You run a regression, and then give E-stat. Now this is how you do it in R. To rectify, rebuild the model with more independent variables, or transform the variables using a box-cost transformation. Box transformation is a mathematical transformation of the variables to make it approximate a normal distribution. Often, doing box-cost transformation of the y variable would solve the problem. Alternatively, you use what is called as a weighted least squares, a more difficult option but superior when you can make it work right, is to use the weighted least squares. And the consequence of heteroscedasticity, it does not bias the parameters. The standard errors are biased when heteroscedasticity is present. So this in turn leads to bias in the statistics and also in the confidence interval. So now the Bruce-Pagan test. Now let us do the Bruce-Pagan test. Now the Bruce-Pagan test can be done with software. But a simple way of doing Bruce-Pagan test is to regress the square of the error on all the independent variables. Okay, you can square the error, and I'll do that regression for you. I will take a regression data analysis. I go to regression. I say okay. The dependent variable is the square of the error. The independent variables are the variables themselves. Only the independent variables, x1, x2, x3, x4. Okay, so I select it. I select the labels and I say okay. Okay. And in the Bruce-Pagan test, you have to check whether the independent variables are significant. None of the independent variables are significant, so one tends to suspect that the problem doesn't exist. However, to confirm whether the Bruce-Pagan test exists or not, you calculate an F statistics, which is calculated as F statistics, which is calculated as mean sums of squares due to regression divided by n minus k. So there are 5 parameters divided by 4 divided by mean sums of squares due to error. I'll put the numerator into a bracket so that there is no confusion. Divided by denominator, I'll also put in a bracket so that it's divided by n minus p minus k. So n is 20, p is 5. So n is 20, p is 5. So 15 minus 1, 14. Yeah, p is 14. And for Bruce-Pagan test to exist, then n minus p minus k at the degrees of freedom, this should follow an F distribution. This is a calculated F. We should compare it with the table F with the 2 degrees of freedom. So you can say equal to F I N V, open a bracket, F I N V, open a bracket, it asks you what's the probability. So we will take a 5% level of significance. It takes a first degree of freedom, which is equal to 5 minus 1, 4. Second degree of freedom, which is equal to 14. And we close the bracket and we get the table F4. The table F4 is less, the calculated F4 is less than the table F4. Therefore, the test is significant. There is no presence of heteroscedasticity at all. Right? So, this is called the Bruce-Pagan test. Yes, we'll come back to diagnostics. So, strictly speaking, there is no presence, and that is called the Bruce-Pagan test. There's another test called the Goldfeld-Quant test. So, in the Goldfeld-Quant test, the procedure is more or less the same. It's just that the independent variables, that is, you regress the error squared. In the Goldfeld-Quant test, you will introduce 2 zeros. You should include here y hat and y hat squared. Okay, so here I will take y hat as it is, that is the estimated value which we calculated, and I will also square the y hat. I'll say y hat into y hat. Into y hat. So you get y hat squared. So these 2 variables Now I run a regression. Of error squared on y and y hat squared. Y hat and y hat squared. So I'm using R. So I'll come to data analysis. I will come to regression. My dependent variable is already set. My independent variables would change. The independent variables become y hat and y hat squared. So I'll run it. And I will say OK. Again, the test is the same. So here I will use a slightly different test. So here also I will do the same. So equal to Regression means of squares due to regression. Divided by n minus k, which is 4, divided by mean sums of squares due to error, divided by 14. So this is a table f squared to values. It's not significant, and therefore we conclude that there is no heteroscedasticity in the data. Okay, there is no heteroscedasticity in the data, and the data is set. For the first assumption is valid. The second assumption is the assumption of multicollinearity. So we shall go back. Second assumption is the assumption of multicollinearity. The independent variables are interdependent, and actually they should not be. If the that means the covariance xi xj should be equal to 0. And for this we use a test called the variance inflation factor. Now the variance inflation factor is a test that is done in order to test multicollinearity if there is multicollinearity in the data. I'll just show you how that looks. So, okay, I have not told you how to do the box cost transformation. Now the box cost transformation is a transformation you would do if you had multicollinearity. If you had heteroscedasticity. So heteroscedasticity can be corrected using box cost transformation. So box cost transformation is a mathematical transformation of the variables to make it approximate to a normal distribution. Now let us have a look at this data. Now I'm just showing you because it's not it's not having that problem. So let me take the dependent variable and I'll paste it over here. I'll take the dependent variable, take it over here, and see what distribution does it follow. For that I should get the maximum value. And I should get the minimum value. And then I'll make it into 5 class intervals. So equal to, I'll make it into 5 class intervals. So it will be equal to, so before that I should find out the class interval. So the class interval is calculated as maximum minus minimum divided by, assuming that I'll have about 4 classes. So I'll have, each class will be about 50. So I'll start with the minimum, 35. And then the next class interval will start from 35 and it will end at 47. Now I'll fix this with F4 because I'm going to drag it down 4 times. So we get 82. The next one, all the 4, the last one will be 176. And the highest one will be 223. So now I'm going to fit a frequency distribution of this data. So how do I do that in Excel? I select a range of values adjacent to the frequency intervals or the class intervals, and then keeping it selected, I type equal to frequency FR EQUENCY, open a bracket, and it's asking where is your data. So I want to do a frequency distribution of this values. I do a comma, and then I get the data. Now I get the free class intervals. I close the bracket and Control Shift Enter because it's again an array. So you see, this is the distribution of the data. So it doesn't look very skewed. So what I'll do to get a plot of this data, I will do a graph. I'll do an XY graph. It hardly looks normal. It's not a very, oops. No. Oh, sorry, I made a mistake. Let me do it again. Frequency, this data, range, close the bracket, control shift enter. Yeah. So it's not a very normal distributed data. Ideally, a normally distributed data should have this feature. So I'm going to generate a normal distribution using the details provided over there. So how I generate a normal distribution is, first I will generate a series of random numbers. So here what I'm doing here is I'm simulating a normal distribution. I'm simulating a normal distribution of the same length of data that I have. Right. And I say equal to norm inverse. So probability is the random number. The probability is a random number. The mean is, I should have calculated the mean. I can do a mean over there. And I will calculate, I need a standard deviation also. I'll keep the standard at 53 and 54. I'll close the bracket, enter. So these I will fix it. I'm taking an average of the data. So the mean of these dependent variable is 124 and standard deviation is 62.5. So based on that, this would be the generated data. Just generating a data set, simulating a data set. And now I will calculate the frequency distribution of that. And that would be, again, I will find out. Okay, I will find out the mean. I'll calculate the average. Keep it down. I'll calculate the standard deviation. I'll calculate the standard deviation. And close the bracket, enter. And now I'm going to simulate the data with this mean and standard deviation. So my command will be equal to 3. I'm going to now, I've simulated it already. I've simulated there. Oh, so yeah. So this is the mean and standard deviation. So I don't require this. Okay, I've simulated the distribution with that mean and standard deviation. So now I will now create the maximum of this range, and I'm going to stack it into a distribution. Okay, and I'm going to calculate the minimum also of this data set. I close the bracket, minimum, and then I get the class interval, which is, open a bracket, maximum minus minimum, close the bracket, and divide it into 4 class intervals. And then I will generate the data over here. So equal to minimum value. And the class intervals will be from the minimum value to the class interval, which I will fix with F4 and add it until I get the maximum value 206. I will drag. One more. 231. So 231 is the maximum value, and now I'm going to create a frequency distribution equal to frequency. I'll open a bracket. So now I'm going to get the frequency distribution of this data, right? This data. for these bin ranges. So I'll close the bracket and Control Shift Enter. Gives me the frequency distribution. Now when I plot this, now this is the actual, my theoretical frequency distribution will be like this. So insert XY and XY. A little bit of a problem that is creeping in with this data, so I have to really think about a mistake somewhere. So I'll have to find out where that mistake is. Right, so I'll have to see right from here where the mistake is, but we should not give me a frequency distribution of this type. This is the actual data, this is the actual data. So this is the frequency. Yes, it's giving me a theoretical distribution, which I'm then going to put into a max and a min. And it's max minus min divided by 3. So I start with the min and I come up to the maximum value. I select this. Okay, so it's not really a good example. Anyway, I think I'll show you that example a little later. I'm a little wary of that. Okay, so we shall move away and we'll move on to the next, which is called as a multicollinearity. The multicollinearity can affect any regression model with more than one predictor variable. It occurs when two or more predictor variables overlap so much in what they measure that the effects are indistinguishable. I've discussed this later. Now I'm going to now show you how multicollinearity is tested. Now to do multicollinearity is the interdependence between the independent variables. So the formula for multicollinearity is Ri. So you get a VIF for each variable. You can see VIF for x1 is equal to Ri squared divided by root of 1 minus Ri squared. Okay, so now we will see how that is done. Right, so I will go back to the data. So now these are my independent variables, x1, x2, x3, x4. Now I'm calculating the VIF for the first variable. So how I calculate the VIF is I run a regression. Data analysis regression. So here my first dependent variable will be the variable for which I am trying to calculate the VIF. So that's my dependent variable. Independent variables are all the other independent, that is x2, x3, x4. So I close it and I run. Now I get a regression output. I don't worry too much about the coefficients. I straight away go and pick up the R squared. I calculate the R squared. Okay, I'll come back to this restricted least squares. Okay, I'll come here. And this is my R squared. It's not R squared. It is Ri squared. Ri squared. Okay, that's for the first independent variable x1. So the formula is equal to, so I'll calculate the value and paste it over here. That is my R for the first independent variable. So similarly, I'll get this for the second. For this is R1 squared, R2 squared, R1 squared, R2 squared. R3 squared and R4 squared. So I'm going to show you only R1 squared. So R1 squared is the regression results that I get when I regress x1 on x2, x3 and x4. My value is 0.06. So the VIF value corresponding to this will be equal to r squared divided by, open a bracket, square root of 1 minus r squared, close bracket. So I get a value of 0.06. So it's r squared divided by square root of 1 minus r squared. So I get a value. So it's very low. So now if this value is very high, if its value is very high, more than 8, will that variable be eliminated from the analysis? To give you an example, supposing I calculate the r, supposing I get an r squared value of 0.9, I get a value of 0.9. Suppose this is only hypothetical. So my formula would be r squared divided by SQRT of 1 minus r squared. And I get a value r squared divided by square root of 1 minus r squared. 1 minus r squared. So 2.8. Let's take a value of 0.95. So 'There's a mistake. There's a small mistake. Let's just check. Oh, 1 minus 1 over r squared. Sorry. There's a mistake. I'm so sorry. There's a mistake. If I stand corrected, the formula would actually be, the formula would be 1 divided by 1 minus r squared. So I stand corrected. Excuse me, apologize for the mistake. So the formula would not be r squared, it will be 1. So this is not a problem, but this would definitely be a problem because r squared is very high. So we get a value 1 divided by, there's no square root either. So get a value like 20. So the formula is 1 divided by 1 minus r squared. There's no square root either here. So you have to take out the square root. So it's actually 1 divided by 1 minus r squared. This is formula. This is VIF. Sorry, I made a mistake. So the formula is, so this variable is not a problem. If this r squared were to even 0.9, even this variable with 0.9, it will get eliminated because of the VIF value. So this variable will get eliminated in the regression to overcome the problem of multicollinearity. So this is how the multicollinearity is done. Now we move to the third thing, which applies only to time series data. So in time series data, what we do is we do a Durbin-Watson t statistics. So in the Durbin-Watson t statistics, what we do is we calculate the autocorrelation coefficient. So the Durbin-Watson, assuming, let us assume for a moment that this is time series data. This is time series data. So just let's assume this is time series data. So I will write ET, which is the error. ET, and here I will have ET minus 1. Okay. So the error terms would be, the error term is here, and I will drag this down. So I've got all the error terms. The error terms the same as what we defined here. So this will have a previous error. So the previous error, if this is, the previous error of this is 32. So I can just do it directly here. So there's no first value. So I do this thing, I calculate the previous value, which is error 32. And I drag it down. Control D. So if I take a correlation of these two, I get the error correlation, or it's called the autocorrelation. So I go to data analysis, I go to correlation, I say OK, and then I have to select both the data points. It is here where the first data is missing, and I say OK, and I ask it to give me the correlation. Will come in another sheet. The correlation is minus 0.4. The correlation is minus 0.4. Okay, the correlation is minus 0.4. So come back here. So the correlation rho, which is rho, it is called rho, is minus 0.4, right? So from this we calculate the Durbin-Watson statistics, dW stat, which is equal to Durbin-Watson statistics is equal to 2 into 1 minus rho. Into 1 minus rho. So the thumb rule, the rule of thumb for autocorrelation is this value should lie between 1.6 and 2.4. It should lie between 1.6 and 2.4. So strictly speaking, this data has autocorrelation. If it were time series data, this data has autocorrelation. The only difference between the regular data and the cross-section data and time series data is time series data is collected over a period of time. So if this data was collected over a period of time, then we have a problem of autocorrelation, which is indicated by this thing, and we have to do what is called as a Cochrane-Orcutt test. So in Cochrane-Orcutt test, what we do is we subtract yt, we create a new variable y dash, and we can construct new x variables called x1 dash, x2 dash, x3 dash. So y, I'll just calculate y dash, okay. Y dash, I'll calculate only this for illustrative purposes. I'll leave the first value. So y dash is calculated as yt, that is the current value of t, minus rho into yt minus 1. So since rho is a constant, I will fix it with f4. Okay, rho is a constant, so it gets fixed. So you can calculate this downwards. And this becomes your dependent variable. Same way, I will just show you how you do the first independent variable. So it's xt minus rho, I'll fix it with f4, into xt minus 1. Right. So this becomes your x1 dash. Right. And this is dragged down. I'm just showing you for illustration. Similarly, you do for all the variables. And now run a regression of y dash on this thing. Check for autocorrelation. And if this value comes within 1.6 and 2.4, then the problem is solved. Your coefficient is unbiased. So that brings us to this thing. This is this procedure. And of course, the last one is misspecification. So the Durbin statistics, dW is equal to 2 into 1 minus rho. This is a formula for the Durbin-Watson statistic. Okay, so that's about autocorrelation. Misspecification bias, as I mentioned earlier, is something which is theoretically determined. The independent variable is not truly exogenous, like one of the finite sample properties which we discussed earlier. Okay, now we have gone through this whole process. We've gone through this whole process of testing the regression coefficients and then determining whether they were significant or not. So that brings us to what is now called as the asymptotic properties of OLS. And by asymptotic properties of an estimator, we mean that that we mean that property we mean properties that are true when the sample becomes large. So whatever properties that it has for a small sample should apply for a large sample. And that is what you mean by asymptotic properties. To illustrate, let x1, x2, x3, x4 be the random sample uh, from a distribution with parameter theta. Then theta hat will represent the maximum likelihood estimator of S. So by asymptotic properties, it means that what you estimate from the sample of x1, x2, x3, x4 will be representative of the population parameter theta. So what you estimate is theta hat, but that will be true of the theta. That is what you're really trying to estimate. So an estimate is blue. If now you call an estimate as best linear unbiased estimate if they have the minimum variance. Okay, so according to the Gauss-Markov theorem, it says that the OLS estimators and MLE estimators are blue, and when they are blue, they have minimum variance, they are unbiased, and they are consistent. And that is what the Gauss-Markov theorem tells us. So this is what it is: consistent. So it's consistent rather than unbiased. So an estimator for a given parameter is said to be consistent if it converges in probability to the true value of the parameter. Meaning, if you get a value of b, as you increase the sample size, that value will get closer and closer to the real value of beta. We now look at the properties of OL estimator that holds in large samples, or more precisely, as the sample size of n tends to infinity, keeping the number of explanatory variables k fixed. The idea that at least for models estimate using large data samples, these asymptotic results will provide a useful approximation to the behavior of our estimator and test statistics. The power of this approach is that we can establish useful asymptotic results under much weaker assumptions than those needed to show that the OLS estimator is unbiased and efficient in the classical linear regression. So when we estimate the OLS, the B OLS by method of, it is consistent, meaning that the B OLS will be equivalent to the beta parameter. So all OLS estimators, if they satisfy the condition of homoscedasticity, no multicollinearity, and no autocorrelation, the coefficients are unbiased and the variance of the estimator B will be minimum. And of course, there's a asymptotic normality, and we can start by considering a sufficient set of assumptions for the OLS estimator suitably scaled to have a limited distribution that is normal. So this is a weak condition, but it's not absolutely necessary. Those as we've discussed. Then we have the concept called as the R squared and the adjusted R squared. The R squared is just the regression sums of squares divided by the total sums of squares, and the R bar squared is the sums of squares due to error divided by sums of squares due to total. So here it is n. This is sums of squares. This is mean sums of squares. So it's actually the mean sums of squares due to error. So what it's really trying to say is, if in an ANOVA, your R squared, if your R squared of the regression is that, you can see that R squared of the regression is regression sums of squares divided by total sums of squares. Right? The R bar squared squared, we can go back and recollect. The R bar squared is sums of squares divided by n minus b, the total sums of squares divided by that, so that we can get it over here. So we haven't got the total sums of squares, so we'll get the total mean sums of squares due to total, the sums of squares divided by the total So the R bar squared may not be a great example, but the R bar squared is obtained as the mean sums of squares due to error divided by mean sums of squares due to total. So you get this. Sums of squares due to error, sums of squares due to error divided, 1 minus, 1 minus that. So we just apply that formula. I've not applied it correctly. So it will be 1 minus, and we get a value of 0.05, because this is only hypothetical data, so we don't expect it to be very correct, and therefore we do not really vouch for these results. But yet we just wanted to demonstrate how these various tests of regressions are done, looking at using these data. So we've examined all these except for, of course, Cox, which we'll then. Now, another very important problem that we face in data is when the data has outliers. Now, the data has outliers. When the data has outliers, then we have to be able to detect them. So outliers are, you have an outlier. So the usual terms are, you have an outlier, and there's a concept called leverage, and there's also a concept called influence. So an observation with a large residue is an outlier. So an observation with whose dependent variable value is unusual given its value of its predictor variable. An outlier may indicate a sample peculiarity, or may indicate a data entry error or other problem. So you can get an outlier. So an observation with a large residue, an observation whose dependent variable value is unusual given the value of its predictor variable, it's also called an outlier. Then there is a concept called leverage. Leverage, an observation with an extreme value of predictor variable. So leverage is a measure of how far an independent variable deviates from its mean value. So these leverage points can have an effect on the estimated regression. So that's basically what it is. So to just illustrate what you mean by leverage, now supposing you were to plot, to this I will add this x variable just because we cannot plot in more than 2 dimensions. So let me just place the data here, and alongside I will take the dependent variable and do a plot of that as well. Right? So I will, sorry, dependent variable should be on the right hand side. So therefore I'll rearrange it on the right hand side, and I will get the dependent and independent variables together. So I will say insert, I will impose a graph, xy scatter, and then I'll show this xy. Oops. Insert xy, and I just put the points. Okay. Now, since the data is hypothetical, you really can't make out any relationship here. There are lots of outliers, if you ask me. But let me generate another data set. This probably doesn't indicate. Let me take another data set where it's a little more structured. That I'd say. Okay, so I now get a plot, xy plot of these two. So I'll insert, I go to an xy plot, and I'll get a line, hopefully. Okay, that's my line. That's my relationship. But supposing I get a value like, say, 72. I'm creating an outlier here. So okay, you can see that this is an outlier. All right, that doesn't look good. So I undo that and maybe give a big value here, 90. I'll just show it as a dot. This is an outlier. So if I take the difference from the estimated value, I'll get a huge error term. And looking at the error term, I can determine where I've got an outlier, which is an outlier, so on and so forth. Okay. So I mean that would be one way of doing it. Similarly, I can give another value like 3.5. This is an independent variable. I can give an independent variable which is very, very high. Okay. So this is called a variable. Now we can say from this, we can also say it's an outlier. And we can also say that this outlier can influence the value. And that is why we also refer to it as influence. Influence. So we call it a leverage. Okay. So influence. By influential observations, we mean influential observations, one or several observations whose removal causes a difference in the conclusion of the analysis. Two strategies for dealing with the fact that least squares is not resistant. Use an estimating procedure that is more resistant than the least squares, and don't try to worry about the influence problem. Use least squares with the strategy defined below. So this is what you do when you have a variable which is going to influence your results, because then when it influences your results, it can also turn out to be wrong. So do conclusions change when the case is deleted? Now, a particular variable has been deleted. No. Proceed with the case included. Study to see if anything can be learned. But if it is going to change, if the conclusions are going to change, is there a reason to believe that the case belongs to the population other than the one under investigation? Because sometimes you may notice that a particular outlier may be actually genuine. Like if you take banking data and if you take deposits of banks, you'll find that there will be one outlier, and that is State Bank of India. So it is not a abnormal value. It is just a value that has to be there. So it says that yes, you must include it. And once you include it, okay, is there reasons to believe that the case belongs to a population other than the one? So do you feel that it is? If it is not, then you continue. If you think yes, does not belong here, it is an abnormal value, then omit the case and proceed. So this is the pro. Don't omit it just like that. Like State Bank of India, I will not omit because I know it is part of the population under investigation. Then the next question is: does the case have unusual distance explanatory variable values? Unusually distant explanatory, does it create so much of a difference? If it is yes, omit the case and proceed. So this is what you have to do. So when you do your analysis, you may have to take out State Bank of India because it could create this problem. Report conclusions for the reduced range of explanatory variables. So you talk about the results as being applicable without State Bank of India. If it is not, then it's more data is needed to resolve this question. So this is basically how you deal with influence, right? So this is what you mean. That should I exclude it? So this is definitely an outlier. Now, how do we detect outliers? Okay. So we'll continue. So now what are we going to do? So now these are very important concepts. So I shall remove all these because I don't need this. I just need the error. This could create a problem, I guess. Okay, I do not need all this. I shall remove it because it can be redundant. Okay. Now let me start. Now, this is my y hat value. This is my error. So let me simulate an error in this. Since it's all formula, let me introduce. Now you see this is the error term. So you can see, have a look at the error terms. So I do an insert, and if I do a line and the line graph, gives me a kind of error. This is my error distribution. There are no outliers, apparently no outliers, as the data looks perfectly all right. Now let me introduce an error. By mistake, this 11th case, the value has been mistakenly entered as 1030. It shows up as a very large error. It will show up as a very large error. So merely inspecting the error, one can determine whether the data has got errors or has it got outliers. So you're looking at the errors, you can determine that. Okay. So that's one way of detecting the outliers by looking at the error terms. But here we should introduce some very new concepts which were not talked about hitherto. Okay. So we have something known as an error. Well, I'll write it away. This is called error. It's called the normal raw error. It's called the raw error. Raw error is calculated as y minus y hat. It's called the raw error. Okay. Then you have something called as a standard error. Standard error. Now the standard error is calculated as error divided by mean square error, sigma e. As I told you earlier, sigma e is this value. It's the square root of this value. So I have to take divided by of sigma e, which is derived from the ANOVA under mean sums of squares due to residues. So you get another error which is called the standard error. It's called the standardized error. This is raw error. This is called the standardized error. I should have fixed it because that shifts along. So it's called the standardized error. Right? It's called the standardized error. And you have another very powerful error which is called the studentized error. Studentized error. It's called the studentized error. The studentized error has one more step of calculation to be done. Now we must develop what is called as a hat matrix. We must develop what is called as a hat matrix. Since now you're already familiar with hat matrix, you will understand it a lot better. Right? You have something called as a hat matrix. Let me show you what a hat matrix is. Yeah. This I shall discuss in the next class. Thank you.